In this session, we talk about the log mean temperature difference. If we look at the general expression for heat transfer in a process, we have this equation Q equals U A delta T min. Now we use a mean temperature simply because in a heat exchanger, the temperature difference between the two streams does not remain constant. So we need to use some mean value of the temperature difference. Now in log mean, we use this mean temperature to be what is called this logarithmic mean, defined as delta T1 minus delta T2 over ln delta T1 minus ln delta T2. Now the question is why log mean? Where did this expression come from? Now to look at this, we need to think about the temperature difference within a heat exchanger. Now if we look at the temperature difference, we plot the temperatures against the length of the heat exchanger. Suppose it's a simple double pipe heat exchanger. We can get the hot fluid temperature to be something like this, or this, or this. There may be several variations among the same types. And for the cold fluid, if you are considering a parallel flow, the temperature may change like this, or this, or maybe other forms similar to these ones. Now in this equation, delta T1 and delta T2, that's the temperature difference between the cold fluid and the hot fluid in the two ends. So if we define this end to be end 1, this to be end 2, then the temperature difference between the two fluids and this end, that's defined as delta T1, and here the temperature difference between the two fluids at this end defined as delta T2. Now the question arises, this delta T log mean depends only on the temperature difference of the two fluids at the two ends of the heat exchanger. So does it really matter how the temperature of the two fluids change inside the heat exchanger? Or there are some assumptions. So to go to the assumption, let's look at a typical temperature profile inside a parallel flow heat exchanger. So if you draw the temperature profiles, the temperature of the two fluids along the length of the heat exchanger, you may get for the hot fluid, the temperature goes from here to here, and that for the cold fluid, the temperature may change from here, something like this. Now let's use some notation here. We'll use Q to be the heat transferred, total heat transfer between these two fluids from one end to some point in the heat exchanger. So that's total heat transfer between one end to some point in the heat exchanger. We'll use the notation capital T for the temperature of the hot fluid and a small t for the temperature of the cold fluid. You'll use the notation Q, capital Q, for total heat transfer in the heat exchanger. And we'll use AT, total area of heat transfer. And we'll use the term A to denote the area from one end to certain point. So suppose if I take this point here, the area between one end that will consider the 0 n to certain point, we will consider that area to be A and the cumulative heat transfer to be Q. Now if we take a smaller segment of the heat exchanger, suppose I take this, a smaller area. So here I can take the heat transfer to be dq, and the area, the differential area I take to be dA. So this is the temperature of the hot fluid, this is the temperature of the cold fluid. So the temperature change of the hot fluid, that's given by dT here, the temperature difference of the cold fluid, that's given by d small. Now we can write this for segment dq equals u dA delta T. Now delta T is the temperature difference between these two fluids at any point. Now for the cold fluid, heat taken can be written as mc CPC dt, where m is the mass, Cp is the specific heat. When we use the subscript C and H for the hot and cold fluid. So you can write it for this hot fluid as mCp dt again for the hot fluid. Now here comes the point of the assumption. What are the assumptions behind deriving the log mean temperature difference equation? Assumptions made are: number one, Cp constant, meaning that for the hot and the cold fluid, the specific heat remains constant. Number two, the flow steady, meaning the m is constant and always either in the co-current or counter-current direction. There is no flow reversal. So the flow rate is constant. Number three, no heat loss. So we get amount of heat given by the hot fluid is taken by the cold fluid. And number four, we assume the overall heat transfer coefficient remains constant. So these are the four assumptions made in deriving the expression for the log mean temperature difference. So what does really these four assumptions mean? Now from the third assumption, we get dq. So the temperature given by the hot fluid is taken by the temperature taken by the cold fluid, and that equals dq. Now if I take both m and Cp to be constant, I can write for this case dt over dqc to be constant and qc equals q. So we'll write dt over dq to be constant. The same way I can write for the hot fluid dt over dq to be constant. Now we have seen from the assumptions that d capital T over dq, that's a constant, and also this small t over dq, that's also a constant, meaning that the temperature of the hot fluid and the temperature of the cold fluid both are linearly dependent on q. Now we know that delta T is nothing but T minus T at a point. So if capital T is a linear function of q, also small t, that's the temperature of the cold fluid, that's also a linear function of q, then it makes sense delta T will also be a linear function of Q. So we'll have, so if T and small t both are linear function of Q, we'll have delta T will also be a linear function of Q. So this one will define the delta T at end 1, and this one will define the delta T at end 2. So then the slope of the line, we can calculate d delta T over dq from these 2 points, delta T2 and delta T1. So if we take the total heat transfer to be capital Q, so we say Q is the heat transfer up to certain point. So that's also cumulative value, but up to certain point in the heat exchanger. But capital Q, that's the total heat transferred. So we can get from N1 to N2, total heat transfer is given by the capital Q. And if the temperature difference at the both ends are delta T1 and delta T2, then we have the slope of the line can be calculated from these 2 points. So also we get dq, the heat transfer within the differential area, we defined it by U dA delta T. So if we substitute it over there, we end up getting d delta T over U dA delta T equals delta T2 minus delta T1 over Q. Now using the assumption that U is constant, meaning it's not a function of delta T, we can write d delta T over delta T plus delta T2 minus delta T1 over Q and U dA. Now if we integrate this equation, we'll integrate it over the limits. Now what would be the limits here? Now if we consider integrating from one end to the another, the delta T1 to delta T2. Now from one end to the another, if we start counting the area will be from 0 to the total area, if we remember it by a t. Integration of 1 over x dx is ln x, so we get ln delta t, limit delta T1, delta T2. We'll get on the right hand side, we'll have this term is constant, this constant, this constant. So we'll have a 0 to a total times the constant term there. Now if you simply rearrange this equation, you will be able to write Q equals U a total delta T2 minus delta T1 over ln delta T2 minus ln delta T1. Now if we compare this equation with our equation Q equals U total area delta T mean, so this mean is our log mean, so we call it log mean equals delta T2 minus delta T1 over ln delta T2 minus ln delta T1, or you also can write it as delta T2 minus delta T1 over ln delta T2 or delta T1. You see that this same as delta T1 minus delta T2 over ln delta T1 minus delta T2. So you see that it does not matter how we define end 1 and end 2, so that becomes arbitrary. As long as you define these two ends to be 1 and 2, you can use either form of this equation. So that's the formulation for this delta T log mean. Now let's look at an example on how to calculate the log mean temperature difference. So we're given the temperatures for methanol, which is the hot fluid. So its inlet temperature is given as 95 degree centigrade and outlet is given as 50 degree centigrade. Now for the cold fluid, which is water, its inlet temperature is given as 25 degrees centigrade and outlet temperature is given as 40 degrees centigrade. We're going to calculate the LMTD for parallel flow and countercurrent flow. Now just to give some consistency in the notation, we'll use capital T for hot fluid temperature. We'll use the small t for cold fluid temperature. Now let's look at the condition for parallel flow first. Now if we draw the temperature profile along the length of the heat exchanger, and this is our temperature, you can denote either end to be 1 or 2. We'll consistently denote the left end to be 1 and the right end to be 2. Also, we'll consistently maintain the notation that the inlet for the hot stream, that's at 1. So we'll take that hot stream is coming at end 1. So this one is the hot stream, and T, this will be 1. So the hot stream going out on the other end, so the out condition for the hot stream will be T2. So again, consistently we'll maintain the notation that the 1 is the inlet for the hot stream. Now for the cold stream, now we're considering this is a parallel flow. So just we don't know what's the temperature profile in between. However, we'll just simply assume that it's something like this, just to indicate the direction of the fluid flow. Now to have a parallel flow, we see that the cold stream should come also this end. So the inlet end for the cold stream is also end 1. So this is also our T1. And the outlet it has N2, so this is our T2. Now we don't know what's the temperature in between. However, just to indicate the direction, we'll assume some profile in between. However, that's not necessary. So when I'm defining this, so we have the 3-step procedures. The step 1, identify the temperatures. So for this we get T1 equals 95 degrees centigrade, T2 the outlet for the hot, which is 50 degrees centigrade, T1 is the inlet for the cold at 25 degrees centigrade, and T2 outlet for the cold, that's 40 degrees centigrade. So step 1 is just to identify the temperature. Now step 2, to calculate delta T1 and delta T2. Now for this case, simply we get delta T1 is the temperature difference at end 1. So delta T1 equals this. So T1 minus T1 gives you 95 minus 25 degree centigrade equals 70 degree centigrade. And delta T2, again this T2 minus a small t2. So that's give you 50 minus 40, 10 degree centigrade. Now when you have it delta T1 and delta T2, rest is just to plugging into the expression for the log mean temperature, which is given as, so we have delta T log mean to be delta T1 minus delta T2 over ln delta T1 minus delta T2. So we'll have 70 degrees centigrade minus 10 degrees centigrade over ln 70 over 10, and that will give you some value 30.8 degree centigrade. So for the parallel flow, we get a temperature delta T log mean to be 30.8 degree centigrade. So for countercurrent flow, if you draw the diagram, we'll have again these are end 1, these are end 2, this is the length of the heat exchanger, and that's our temperature. Again, we maintain the notation that 1 is the inlet for the hot stream, so outlet will be here T2. And now is countercurrent flow, so the cold stream should come from the other side. So cold stream is entering over here. So T2 This is the inlet temperature for the cold stream. Do remember that T2 here is inlet for the cold stream. Here T1 was the inlet for the cold stream. That's the difference here. Okay. So the outlet will be again this side. So T1. So T1 now is the outlet for the cold stream, where small T1 was the inlet for the cold stream for this case. That's the difference. So you can have some idea about the temperature profile here and there. So we have defined this temperature now, and so step 1 will be just to define the temperatures. So we'll have T1 equals 95 degrees centigrade, T2 equals 50 degrees centigrade. This remains the same. We'll have now T1 equals 40 degrees centigrade and T2 equals 25 degrees centigrade. So our definition for delta T2 and delta T1 remains the same. However, because of these values, we'll have delta T1 equals T1 minus T1, a small T1, which will become now 55 degrees centigrade. And delta T2, again T2 minus a small T2, which will become 25 degree centigrade. Now when I have defined these two for the delta T log mean, this case will be, the definition remains the same, delta T1 minus delta T2. So we'll have 55 minus 25 degrees centigrade over ln 55 over 25. So if we just simply do the math, we'll end up getting 38 degree centigrade. So now the final comment on that is that for parallel flow we got a value of 30.8, in a counter current flow we got a value of 38 degree centigrade. So this will be the case always. The log mean temperature difference for the counter current flow is always higher than the log mean temperature difference for the parallel flow for the same inlet and outlet temperatures of the hot and cold fluid. Now let's look at how to calculate the log mean temperature difference for a shell and tube heat exchanger. Now if there is only one shell pass and one tube pass, you can use the same procedure described earlier for the double pipe heat exchanger for both counter current and parallel flow. However, if either or both of the shell side and the tube side has multiple passes, in that case we need to use another technique. This is an approximate method to calculate the LMTD for shell and tube heat exchanger for multiple pass. So the problem arises because if you look at here, suppose for a 1-2 shell and tube heat exchanger, here the shell side has one pass and the tube side has two passes. So the cold fluid is through the shell side and the hot fluid is through the tube side. So if I draw the temperature profile for these two fluids, we have no concept of inlet side or outlet side here for the hot fluid, because this to be side 1 and this to be side 2. So hot fluid is coming in at side 1, also going out at side 1. So the earlier concept we described of two sides 1 and 2 becomes invalid for this case. So for such a case, we need to follow an approximate procedure, and it involves 3 steps. So in step 1, we calculate an LMTD assuming a single pass counter current flow. So it doesn't matter how many passes are there, we assume a single pass counter current flow and calculate the LMTD following the procedure described earlier. And then we correct that LMTD by a correction factor. And that correction factor FT, we'll see in details how to calculate that correction factor. So a correction factor is calculated, and then the corrected mean temperature is obtained as just multiplying the LMTD calculated assuming single pass counter current flow heat exchanger by the correction factor. That will give the corrected mean temperature for the shell and tube heat exchanger is multiple pass. So let's look at how to do it using an example. So here again we consider the example that methanol condenser is to be subcooled from 95 degree to 50 degree centigrade, and water to be used as a coolant whose temperature goes from 25 to 40 degree centigrade. If we use a 1-2 shell and tube heat exchanger, we need to calculate the corrected mean temperature for this heat exchange process. Now just couple of notes on the symbols here. We'll use the capital T for the temperature of the hot stream and a small t for the temperature of the cold stream. Also, we'll consistently use 1 for the inlet side of the hot stream. So for counter current flow, 2 is the inlet side for the cold stream. So following that procedure, let's calculate the corrected mean temperature for this process. Now in step 1, we need to calculate the LMTD by assuming a single pass counter current flow. So if you assume that for this particular process, we need to identify the temperature. So that is step I will call step 1.1. So first identify the temperatures. What's capital T1, capital T2, small t1 and small t2. Now we know that we denote side 1 and side 2, and we consistently denote the inlet side for the hot stream to be side 1. So this one is our T1. So T2 is the other side. So that's our T2. So T1 is the inlet temperature for the hot stream, which is given as 95 degree centigrade. So T2 is the exit temperature or the outlet temperature of the hot stream, which is given as 50 degree centigrade. Now for the cold stream, we'll consider counter current flow. So the cold stream is coming in on this side. So a small T2, that's the inlet temperature for the cold stream, and it goes on the other side. So a small T1, that's the outlet temperature of the cold stream. So we'll use this notation. Do remember that in your books or some other references, there may be different way to denote it. So we'll consistently follow this notation. What the temperature profile in between, we don't know, but just for the sake of giving the inlet and outlet direction, we'll just use it something like this to denote the direction of the stream. So we have T1 to be 40 and T2 to be 25. Do remember that T2 is the inlet for the cold stream, small t2, and small t1 is the outlet for the cold stream. So that's identifying the temperature. Now in step 1.2, we need to calculate the delta T1 and delta T2. Now delta T1 and delta T2, the definition is the same. Delta T1 is the temperature difference of the two streams at side 1. So we have T1 was 95 degrees centigrade and our T1, small t1 was 40 degrees centigrade. So this gives a delta T1 to be 55 degree centigrade. Capital T2 was 50 degrees centigrade and a small t2 was 25 degrees centigrade. So we get delta T2 to be 25 degree centigrade. Now using the definition of delta T log mean, what we get is delta T1 minus delta T2. So that's 55 minus 25 degree centigrade over ln 55 by 25. So this will give you a value of 38 degree centigrade. So that's step 1. The second step, how to calculate this correction factor Ft. Now to do it, we need to define two terms, R and S. Now this is the definition of R, the ratio of the temperature decrease of the hot fluid to the temperature increase of the cold fluid. So you know the temperature of the hot fluid changed from 95 degrees centigrade to 50 degrees centigrade. So that's 95 minus 50, and that for the cold fluid changed from 25 to 40, so 25 and 40. So this gives a value of R to be 3. So that's the ratio without any unit. We need to define another term S as the ratio of the temperature increase of the cold fluid to the difference in the inlet temperature of the two fluids. How much was the temperature change for the cold fluid divided by what was the maximum temperature difference in the heat exchanger. So here it should be T1 minus T2. So it should be T1 minus T2, small t1 minus small t2, capital T1 minus small t2. So we have T1 to be the outlet for the cold fluid and the small t2 is the inlet for the cold fluid. So we'll have 40 minus 25 degrees centigrade, that's the temperature increase of the cold fluid, over 95 minus 25. So if we do the simple math, you will end up getting a value of 0.21. Now using these two numbers R and S, we can calculate the correction factor. And how to do it? There are two ways. One, you can use this equation and plug in the value of R and S in this equation will give you the value. Alternatively, you can use this graph. And this graph is available for 1 to x to 4x, meaning that single shell pass or 2 or 4 tube passes, or double shell passes and 2 and 4 tube passes. Do remember that the correction factor does not depend on the number of tube passes, it depends on the number of shell passes. So how to calculate the correction factor here? We have a value of R and S. R we got as 3 and S we got as 0.21. So to remember that the value of S is always less than 1, the value of R can be less or greater than 1. So now we have the value of S to be 0.21. So if we have, this is 0.2, this is 0.3, so 0.21 will be somewhere here. And we see R equals 3, there is no line for R equals 3 here. So you see here that these lines are for different values of R. So we have a value of R for 2.5 and 3.5. So it will be something in between. We can assume a line something in between and draw a line here. And for the value of S to be 0.21, if you want to draw a line up there, the intersection of these two will get the value of Ft. So from here, we can get the value of Ft to be around 0.94. So do remember that these different lines are for different values of R in the increasing direction, and you have the values of S on the x-axis. So take the value of S on the x-axis and go all the way where it crosses the line corresponding to the value of R. You get there the value of the correction factor from the chart there. So we get a value of around 0.94. So in the step 3, the corrected temperature is 0.94 times 38, which give a value of 35.7 degrees centigrade. So that's the corrected log mean temperature for this 1-2 shell and tube heat exchanger. Now a few notes on the value of Ft and how it is used to choose the configuration of the shell and tube heat exchanger. A desired value of Ft is greater than 0.85. So if it's less than 0.75, it's not acceptable. And for this case, we need to choose a different configuration. And you know that for a given shell pass, the value of Ft is not affected significantly on the number of tube passes. So to get a shell and tube heat exchanger with a higher value, you need to choose a heat exchanger with more shell passes. So that's the use of Ft for choosing the configuration of a shell and tube heat exchanger. And finally, in the appendix of this note, you will find how we came up with the derivation for the case where the overall heat transfer coefficient changes linearly with delta T. This, if you are interested, you can look at the note and use the derivation. So in summary, we discussed what is this log mean temperature difference, where did it come from, we saw the mathematical derivation, then we used that definition to obtain the log mean temperature difference for a double pipe heat exchanger for both counter current and parallel flow. Then we looked at how to obtain the corrected log mean temperature difference for a shell and tube exchanger when there are more than one pass. And we saw an example of how to use that method to obtain the corrected log mean temperature for a 1-2 shell and tube heat exchanger. Finally, we looked at what's the use of this correction factor in choosing the configuration of a shell. Thank you.